Hello, everybody. I'm Kalinowski. I work for Espressif as a manager of the IDF core team. And today I'd like to present ESP-IDF Test Framework from, external projects perspective. So I'm going to talk a little bit more on how external contributors, how you can use our internal frameworks for your project's development or for your contributions. Uh, so I will really divide the talk into two parts. The first part is going to be overview of what tools we are actually using, what frameworks, how this all looks in the background. And then in the second part, I'm just going to show some real examples how you can leverage that in your own project. For instance, if you are developing IDF component. So, and in the middle, I'm going to talk a little bit more about prerequisites to do so. So let's start. I just wanted to start with this screenshot. This is a screenshot from GitHub, and if you've ever created a pull request to ESP-IDF repo, this is what you are going to see. And well, there is not much really. You can see there are some checks like pre-commit rules run on the pull requests, and mostly these are basic checks, for instance, code validation, etc. Then you can see this step, which basically says that the sync was approved, and now we are going to run the checks in the internal code base and the license check. So yes, this is all you see externally, and there is much more going on. So I'm always saying that from external contributor perspective, ESP-IDF repo is like a black box. You are submitting PR, and at some point in the future, it gets magically merged. Your commit gets magically merged, and but there is not much in terms of tests, and this is how it looks from inside. That is what you can see below the surface. This is a screenshot of our internal CI, our internal pipelines. We use internally we use GitLab and GitLab pipelines to run our tests, and there is actually quite a lot. In the first column, we run all kinds of pre-checks. Some of them are related to very specific, related to our processes, related to particular parts of the system. Some of them are more generic, like for instance, all kinds of let's say the C-lang tidy check, or we have fast template up test, which is basically building the simplest possible testing application, or pilot test checking Python syntax. So these are all the basic checks, and actually some of them are available and visible on GitHub, but not all of them. In the second column, you can see all the builds we are making. Actually, there is much more to that, because I think every step equals like 5 builds. In total, we have several hundred different builds for different option configurations, different hardware configurations, etc. Then we are building the documentation, and finally we have something called target test. These are all tests that we are running on the target. Last step is something what we call host tests. These are tests that are not running on the target. They are just running on the same machine as a test framework. I will give some more details later. And finally, after going through all those steps, we actually go to the deploy and push to GitHub step. That is when the entire code is validated. The whole pipeline, entire pipeline can take several hours. It's pretty time consuming, and maybe it's one of the reasons that we currently don't make it available on GitHub. Here I'd like to talk a little bit more about different test types. So our naming conventions for test types, well, sometimes may be a little bit different than common naming conventions, but that's why I'd like to explain it here. So first of all, I already mentioned pre-checks, so I'm not going to add much more in here. These are all the basic validations. I mentioned build step, several hundred distinctive builds, documentation build, and a little bit more about unit tests. What we call unit tests internally are not exactly the unit tests. These are just small applications which run on usually on the hardware. They are designed to test particular component, but we don't use any mocking here, or we don't use well, these are not the actual unit tests. The next type of the tests is something we call example tests. So in fact, they are very similar to unit tests. However, these tests are basically covering all the ESP-IDF examples, all the examples we have in ESP-IDF repo. So basically, all the examples code is built and tested on the hardware. And finally, we have so-called integration tests. We call them integration tests because they cover a little bit larger areas. They are designed to test, for instance, Wi-Fi or Bluetooth integrations. Sometimes they include multiple ESP32 boards. So they are much more complex than example tests or unit tests. However, all of those, unit tests, example tests, and integration tests are usually run on the hardware. Then we have final category of tests. We call them host tests, and these are this is actually quite wide category. because it includes all kinds of tests. The tests which could be called unit tests. Well, we are using CMock for unit testing, and they can run actually on, well, these are actually real unit tests because they can run on Linux. We don't require hardware. We just test particular parts of the module. But also, as I said, the host test category is pretty wide. So this test will also include, for instance, toolchain tests, build tests. So yes, this is pretty wide category, and it's very important to keep in mind. Well, this naming conventions. Without that, the rest of the presentation could be perhaps confusing. Okay, now I'm going to go briefly through all the frameworks we are using internally. So here I should actually mention one of the framework we developed is called PiTest framework. It was an internal tool, and basically we are still using it for running most of the tests in our system. However, we are migrating to PiTest. We developed several PiTest extensions to make it easier to test on hardware, to work with ESP-IDF. So here I just wanted to mention, I provide the link to PiTest documentation. You can find PiTest basic packages here, and well, on the right, just as an illustration, this is how a typical test will look like. So it's pretty simple. Here you see PiTest and also our PiTest embedded extensions. And okay, so here we have PiTest embedded set of extensions. You can search PyPy to find all of them. Just look for PiTest embedded. Of course, the most important top level one is PiTest Embedded IDF. It contains all the generic features, generic stuff used by ESP-IDF for testing. And then in this particular presentation, I will mostly pay attention to PiTest Embedded QMU, and also very important, PiTest Embedded Serial ESP. So this extension is actually to make it easy to connect to ESP devices. Well, flash ESP devices and work with ESP devices connected via serial port to your test runner. And well, in addition to that, of course, you can find extensions for Arduino, extensions to improve JTAG experience, and yeah, I think that's all in here. You can also find more information about PiTest Embedded on our documentation page, packages search, and the source code. Source code is here. The next tool I'd like to mention is Unity Test Framework. I'm not going to too many details here. I just want to say that it's well integrated with CMock, because actually CMock and Unity Test Framework, they come from the same place. Also, it's quite well integrated with PiTest, and this is actually part of our work as well. And yeah, what else? I mean, mostly Unity Test Framework is just used to design your unit tests. On the right, you can see a typical wrapper you can find in ESP-IDF. Yeah, I'd like to point out that particular method, expect Unity test output. So in this example, you can see how PiTest is actually, or PiTest Embedded is providing support for Unity Test Framework. So you can have in ESP-IDF, you can have Unity tests, Unity-based tests wrapped in a simple way into PiTest. The next thing I'd like to mention is something we are working on, and that is FreeRTOS Linux simulator. This is under development, but by the time of when this presentation is publicly released, it should be already available for external contributors. So basically, it's based on FreeRTOS Linux simulator. You can find here under this link. So the important to mention here is that the upstream version of Linux simulator, FreeRTOS Linux simulator, supports only unique single core FreeRTOS. So AWS, the current upstream version of FreeRTOS is single core, and there is an effort for developing a multi-core version of FreeRTOS in FreeRTOS SMP branch, but the simulator is not yet ready for that. So what are our goals for Linux Target? So well, I will start from the end. We don't have a plan to support dual cores. We think that the single core support is sufficient to run most of the scenarios that we would like to test just on Linux host. And we want to migrate some tests which we are currently running on hardware to just Linux-based host tests. And that applies to example tests and current unit tests. I will have a little bit more about Linux simulator in our roadmap at the end of that presentation. Okay, the next tool we are using internally is CMock. So CMock is in general is a stub generator for unit testing in C. I mentioned already it works smoothly with Unity Test Framework. And basically what it does, it can parse your C headers and create mock interfaces for your testing. We currently use CMock to generate stubs for our host tests. We don't have any tests that work on target. In theory, it should be possible to run CMock generated tests on target, but we don't have a plan to do so right now. The next important tool or I'm not sure if I should call it a tool, I should mention is ESP-IDF container, and this is extremely important for testing. We are using it internally, and I'm not really sure whether everybody in the audience found that actually our Docker image for ESP-IDF exists, but it's something I'm going to use in the examples we'll have at the end of this presentation, and it's extremely convenient to use for building against particular ESP-IDF version. So you can find our image on Docker Hub under Espressif/IDF. We maintain several versions. So the most recent is of course latest stack, and it's generated for every single commit that's merged into master branch. Then we have an image for every single release branch. And then finally, we have tag. That's the one at the bottom, VXXX, for every single release of IDF, ESP-IDF. So whenever you need to build your application, build or test your application against particular version of ESP-IDF, you can always find appropriate Docker image. So here I have to mention that the purpose of the Docker image, the main purpose is to provide means to generate builds. So the image actually includes ESP-IDF source code itself. It includes appropriate tool chains, and it includes any other tools necessary to perform a build. But it doesn't include any additional tools related to testing. For instance, there is no we don't have a PiTest Embedded, or we don't have QEMU installed inside the container. So this has to be done as an extra. Okay, and I already mentioned QEMU. Basically, QEMU is open source emulator and virtualizer. It works with many hardware architectures. It provides emulation of very large number of peripherals, and what's most important, it has support for Extensa, and it has support for RISC-V. I would like to mention we have links for QEMU projects here, and also this is the repo, the original repo. Here I'd like to mention a little bit more about our own fork. of QEMU. So in order to emulate ESP32 chips, we had to add a few modifications to the original software. They are not upstreamed yet. So we run our own fork on GitHub, Espressif /QEMU, and we are going to use we are using this fork for internal development. We are going to use it in demos in this presentation. We also have our own wiki and information about releases. So on the left, you can see what we are currently supported. We have right now we have support for basic ESP32. We don't have support for any other hardware. We don't have support enabled for RISC-V yet. In terms of peripherals, we of course support all the basic peripherals like SPI, I2C. We have UART support. We have SDMMC host controller support. We also support, well, that's actually partial support for hardware crypto. We have support for Ethernet. And finally, we already have support for if-use. This is our current support. You can find more. Every single release is of course documented, and you can find the details. You can post your issues to our GitHub if you have any particular requirements. Then I'd like to share how you can build QEMU from the source code from our fork, and I'm doing it in the way of Docker file. I think you can see that it's based on IDF latest image. Then we are installing a few additional dependencies. These are actually needed by QEMU itself, but also I think some of those libraries are needed by the test framework itself. So what I do first, this Docker file, I actually install the PiTest and CI. This is not directly needed by QEMU, but it's going to be needed when we actually run the tests. So you can see I just use IDF tools script and install Python environment with PiTest and CI features. Then in the last, 3 steps really, or 2 steps, I'm updating the path in advance, cloning recursively Espressif fork of QEMU, and finally creating directory QEMU extensa, configuring the build, and running the build with extensa targets here. Finally, in the final step, I just go to the newly created QEMU extensa folder and run make install, and that will build all the necessary QEMU binaries. So you can either use the container, or you can follow these steps on your local machine as well. Docker file is available in the sample repo. I will mention it later. Okay, so let's continue. And here we actually reached prerequisites that may be necessary to set up your pipeline on GitHub. So firstly, if you want to run tests on actual hardware, you may need to set up so-called GitHub self-hosted runner. So Espressif provides an example. Well, we actually have entire test template. Inside the test template, we have a document that explains how to perform the whole procedure of creating self-hosted runner. So in this case, the runner is based on Raspberry Pi 4 Model B. You need some ESP32 development boards. In this case, we use DevKit C and C3 DevKit M, and of course SSD card with Raspberry Pi OS. Well, of course, this prerequisites are used in our example, but you can follow the same instructions. You can actually set up self-hosted runner on any Linux machine or maybe even Windows machine. So I think the instructions can be modified to use almost any hardware. Then the document will give you steps to actually add the self-hosted runner to your GitHub repo, or it can be done on organization level, and setting up an agent on the runner itself. Okay, so that's one of the prerequisites. We can continue with sample projects I've created. So the first sample project, that's CXX component. So that's actual C++ component. We've migrated out from main ESP-IDF repo to a separate repository, so it can be installed as a optional component. CXX component has its own GitHub action to run appropriate host tests, and also has GitHub action to run target tests. So this is the repo if you want to check how to set up and use GitHub actions with self-hosted runner and run tests on actual ESP32 hardware. This is the place to go. And the second example is something I'm working on right now. This is basically WebAssembly runtime, also wrapped in a component. And because of the specific of the project, the project is mostly hardware independent. It's a good candidate for testing in QEMU. That's why I've selected this project. Here you can find sample GitHub action for running tests in QEMU, and I'm going to talk a little bit more about this setup in a while. Also, in that repo, you can find the Docker file, which I described a few slides before. Finally, what's important to mention is our GitHub ESP test template. You can find it under Espressif organization on GitHub. The link is available here. It basically provides the basic basic layout for the repo where you have where you use GitHub hosted runner to build your application, your component. Then you use self-hosted runner to run the test on ESP32 chips. And finally, it uses GitHub hosted runner to publish the results. So the CXX component project is actually based on this template. Here is a little bit more about the layout of the project, of the template project, and what we have inside. So in GitHub workflows, you can find GitHub actions definitions. I will show you GitHub actions in the context of CXX component project and WAMR component project as well. We have main folder, which contains the actual component source code. And finally, we have test application project that includes all the tests with the source code, etc. So now I'd like to walk through the repositories I have. I will just show briefly how the project is constructed and all the workflows. So let's start with ESP-IDF CXX project. Well, as you see, it's very similar to template project. There are some subtle differences in the layout. However, in essence, it's the same. So in this particular project, we can find 3 workflows. We have test workflow, test host, YAML. So let me check this one first. As I already mentioned, all the host tests, they don't require the hardware. So the workflow is going to be very, very, very simple. In this case, we just run tests on basic Espressif IDF release 5.0 container. So that's one of the containers I mentioned. And we do that in 2 steps. The first step is checkout master branch. Second step is build and test. So what's important to mention here is actually we are running export.sh, and this is to set up the ESP-IDF environment. That has to be done every time after starting the container. And then we are use matrix of application names. Well, these are the applications we are building. For every application, we perform build step, and then after the binary is ready, we just run it on the local host. That's why we call it host tests. Let's just check the target test. So target test job is a little bit different. In this case, we start with checkout, just like in the case of the host tests, and then we run IDF Build. So what's the difference with the host build and test is that here we are actually building for the target, and the test is done in a separate step. So instead of running test immediately, we upload artifacts in this step. This is still done on GitHub hosted runner. Next step is done on self-hosted runner. So in this case, you can see we specified two targets, ESP32 and ESP32C3, and we specified two test applications name. Here you see that it runs on self-hosted Linux and Docker. Please pay attention to the steps. We are installing a few Python packages manually on the top of base container. So that's PiTest Embedded, PiTest Embedded Serial ESP, and PiTest Embedded IDF. So we need PiTest Embedded Serial ESP, as we'll be connecting to the actual target. I will show you how it works in the output. Finally, you can see how the test is run on the target. So we use PiTest and we specify target. And of course, this is obligatory parameter. We need to use embedded services, that is ESP and IDF. In the last step, we upload the artifacts. And that's, you see, the GitHub action definition is much more complex this time. You can refer to this file if you want to run the test on the target. Okay, let's see how it works in case of real pull request. So here we have somebody created a pull request. Here you can see the build jobs on this particular pull request, and let me check, for instance, ESP. Okay, let's check this one, pull request, ESP event test application. Well, I think build is not particularly interesting. It's the same for every application, for every host or target test. So let me go directly to run test action. Okay, so what's interesting here? As you see, we started the test on self-hosted runner here with target ESP32. In the log, you can see what the PiTest embedded is actually doing. It tries to connect to several serial ports. You see it's connecting and then fails until it's actually successful, USB 0. So PiTest embedded is actually tries to connect to all the ports and find appropriate board which is needed for testing. Then it's flashing the board with our binary. And then finally, in green, you can see how that's the log from the board. You can see initialization. Okay, and here this is actually interesting because the output here is from Unity Test Framework, and this is handled correctly by PiTest. And finally, you can see that two tests has passed. Again, this is all Unity test output from the hardware. and the rest is handled by PiTest. One test, uh, one test has passed. So that's how the uh, hardware tests, target tests look like when running uh, on the custom uh, self self-hosted runner. The next I'm going to show you is WAMR component repo. I skipped host tests as these are pretty simple. You basically build and run the application on the same machine. Here, I'm going to show you a sample repo with QEMU. So you see here we have GitHub workflows as well. In Dockerfile folder, you can find the exact Docker file I was showing you before in the presentation. Let's go back a little bit. Then you have subrepo wasp micro runtime. This is actually what this project is wrapping. Under source file, there is a test. There is a test application. Well, I still call it Hello World example. So we have a test in here that we are going to run, and you see it's actually marked as ESP target is ESP32. The test is host tests, and we also have QEMU marker. The rest is almost the same, except of the device under test, which is QMU DUT. So this comes from Python PiTest Embedded QMU. And well, the test will pass if we get hello world in the log. Under main, we just have a C application. Basically, that application starts the WAMR runtime and also prints hello world. And finally, I'm going to show you the workflow definition for QEMU test. Okay, it's available here under run tests. As you see, it's pretty simple in comparison to hardware test. I'm actually doing everything in a single step, really. I mean, single container that is run on GitHub Runner. I don't need self-hosted runner here. You see, I use the image zimcal /QMU2. So that's the image produced by the Docker file, which I presented. Of course, I do recursive checkout in here. And then finally, in the run step, I have only 3 lines of code. So export, that's the same as in case of CXX example. And then I use our internal script to build applications. So basically, that script will find all the application in this component directory that can be built for a target ESP32, also with QEMU marker. So this step builds my test hello world application, and finally I run the test itself. Then it's very similar to the command we saw in CXX example case. Also, target is ESP32, but I pass QEMU label, and embedded services I use is IDF and QEMU. Well, I have additional parameter which is built by directory. That's about the specific of the PiTest embedded and run outside the ESP-IDF main repo. That's all. Very simple. Let's check how the output looks like. I think in pull requests, I just prepared, well, something failed, but well, pre-commit check. I just set up on this repo. Let me check our QEMU test and what happened here. So we are really interested in that part, running container. Here IDF UI is ready. And finally here you see the test session starts. It finds one test hello world host. Here's some setup. And then finally the device is booting in QEMU. So everything looks exactly as on real hardware in this case. We have some output from WASP WebAssembly runtime. And then finally we have our hello world text. The framework finds the hello world and it decides the test has passed. So that's all about QEMU demo. So we finished our demo, and now I'd like to tell a few words about our roadmap for the future. I divided the roadmap into two parts. I already mentioned that our Linux target is in progress, and it should be already available when this presentation goes public. Then we are going to work do some more work on QEMU as well. If somebody is asking, we are obviously going to add support for RISC-V and to support other ESP hardware than just basic ESP32. And one of the things we are starting to work on is the test coverage for FreeRTOS SMP. So we want this test coverage to be as much as possible migrated to QEMU, and we want to make it public. And the second part of our roadmap, this is something I called our roadmap for GitHub community. As we started the presentation, I already mentioned that when you go to GitHub, when you create pull request, all you can see is the tip of an iceberg. So just some basic tests, and you basically don't know what's happening with your pull request behind the scenes until it's merged after some time or not merged. So we want to make it more transparent. This process should be definitely improved, and it will benefit the community. You can also expect more GitHub actions run, more checks, host tests, testing using QEMU, perhaps also Linux target, and in some cases we may enable even hardware tests on GitHub. Well, as you saw in CXX component, we are already running some tests on real hardware. Then one more thing to mention from our testing perspective, we would like to what's the part of ESP-IDF core and what is not. You could expect migration of some non-essential components to their own repos with their own tests and even their own community. So I think after CXX components, there will be some more non-essential components migrated outside main IDF repo, for instance. I don't know, that could be USB or yeah, you name it. Yes, so I think this all will help to improve the community. Also, we hope this work will improve the efficiency of pull request and merge request processing. And yes, that's the end of my today's presentation. And now we'll be looking forward to questions. Thank you very much, everybody, for attending.